Also, reminder up front to like and subscribe. Thank you.
This ain't what you want. This ain't what you want. This ain't what you want.
Hello, people. Everybody. Welcome back to And Lash. So, today we are doing something different. I'm bringing back we are back with high effort videos today. Today we're going to be doing part 1 of the Iceberg of Math. Now, Wendigoon obviously popularized the iceberg situation a few years back. It's been done since then, but I've never seen a math iceberg. There's kind of a good reason for it too, which is that some of this, like the stuff at the bottom of the iceberg, is just very, very difficult to comprehend and understand, and so it's going to be a challenge for everybody. But I have a math degree. Like I'm a mathematician technically. Like, I've published things and done different things. So outside of somebody with an advanced degree in math, I might be the best you're going to get as a narrator for something like this. So, not to brag, but so I actually have 2 icebergs that we're going to be looking at, and I'm going to be kind of going through them at the same time, side by side. There are some overlaps on them, and then there are not a lot of overlaps on them. So I think we can kind of do both at the same time and just work our way down. So today's going to be the, surface level. I'll show you let's pull up the icebergs for you. This is going to be the first one we're looking at today. Obviously starts with addition, counting, and then our second one, which is, again, like I said, it's similar but different, looks like this. So today we're going to go through elementary school and school level math. That's where we're going to stop. That's going to be our goal, our stopping. And then on this iceberg, we're going to stop where it gets into this white. So this is kind of hard to read, but I'll read it for you. And we're going to go through this together. So something that my roommate pointed out that I should do, which I will be doing throughout this video, is for everything that I'm describing, I'm going to give myself a rating out of 10, how confident I am in explaining that material. Okay, so, because we'll get there, folks, but we've got the Birch and Swinnerton diet conjecture down here. We've got some random matrices, meromorphic functions. See, these are things I know, I've heard about, but I don't know, you know what I mean? So it's going to be, this is why it's going to be an experiment for everybody, and hopefully you'll enjoy, taking this journey with me. So let's get started. Counting. Give myself a 10 out of 10 confidence for that. That is, actually, humans right here, counting's right here. It's the most basic thing you can do. It's just what this goes to that. It's like that old finger game when you were a kid, you know what I mean, where you hit their hit their one finger with your 2 fingers, and then they have 3 fingers, and so they've been doing that since the ancient times, folks. That's counting. It's basic counting. So there you go. Addition. That is, I also give myself a 10 out of 10 for addition. Oh, real quick, fun fact about counting is there's, later down in the iceberg, I don't know if I haven't seen it in the iceberg, but it's there's a whole field of study called combinatorics that is just the study of counting. So, that's fun because this is going to be for, this iceberg video is for people who do not like math, and people who do like math, and everybody in between. So I'm going to try to keep it fun, have some fun facts in here. I'm going to try to make it as understandable as possible, and we're going to and the good news about math and how this works is I'm going to put the whole thing together at the end. We're going to have a long documentary of the entire iceberg, and it will build on itself, and that's because that's how math works. So we're just going to handle it together. I think that everybody can get through it, and for those of you who are interested in math, or maybe think you're good at math and think you might want to study math, I hope that this can be informative and inspirational to you. So that's kind of what's going on. But so counting, also known as combinatorics, it's real fun. But I had a combinatorics class one time. It was very difficult, and that professor was a very intelligent person. But anyway, addition. That's adding things together. 1 plus 2 is 3, 3 plus 3 is 6. But it's counting, but so counting is one operation, and then addition is like concretely defining counting, right? It's a way of like, I would say it's, if you want to think about it in terms of count, now I'm over-explaining it, but if you want to think about it in terms of counting, this lets you count by adding more than just one additional, because that's counting is just going up by 1. So if you want to go up by 2 or 3 or 4, then that's addition. Multiplication is taking, like, I'm wondering if I should draw these things out. This is the worst video in the world so far, but trust me, it's going to get better. All right. Counting. 1, 2, 3, 4, 5. You know those. So that's equals 5. That's counting. Okay. Now we have 3 plus 2. Oh God. I meant to draw a plus sign, and that's totally just a swastika, but we're gonna ignore it. Equals 5. That's addition, folks. Okay, all right. Now okay, this swastika is still on the screen. 3 times 3 equals 9. That's multiplication, because think about like that, right? And like that's 1, 2, 3, 4, 5, 6. You can count to 9, or you can go 3 times 3 equals 9. So that's multiplication. I give myself a 10 out of 10 for confidence on that. And fun fact, that's probably this right here is probably exactly how they first started multiplying, but I can't prove that. Anyway, basic geometry. Okay, oh well, let's do subtraction and division. So subtraction and division, I give myself a 10 out of 10 for each of those. And subtraction and division are the opposites of multiplication and addition. So what's that look like? So we had the 5 that we counted, right? And then that's in groups of 2 and 3, right? We're just, these aren't numbers, they're just sticks. So that's equal to 5, right? And then 5, so that's 2 plus 3. But then 5 minus 2 equals 3. We know, so that's the opposite of addition. Now, 9 divided by 3 equals 3. And that's the opposite of this box thing. We have 9 divided into 3 sections. We just take the middle section here. Say that. Divided into 3 sections, we just take the middle section. That's 3 squares out of the 9 squares, right? Which is, so 3 is left. Division. There you go. And let's real quick go to this iceberg to see if we, okay. We have all that so far. So 2 concepts here will do. Well, let's start knocking some of these out. So we've already covered addition. A number is, I think, goes with counting. It's just the concept that like 1 and 1 is 2. That's a number. We have addition. 0 is the concept of nothing. So, the first people to be doing math, right, didn't believe in the concept of 0, because like, how do you have nothing, right? But then, well, actually, if we go back here, let's check this off real quick. Negative numbers, you realize that like I think the concept of 0 and negative numbers originally, confidence 10 out of 10 on this, by the way. The original concept of them came from debts, because you can like owe somebody money, so you can have negative money. Like I owe my mom money right now. That's an example. So the concept of negative numbers does exist, and negative numbers are real. Whereas the first people to ever do math thought that there could be no number less than 1. Either have 1 of something or you have nothing, and then there's nothing to talk about, but there's not 0. You know what I mean? So, and then the concept of 0 was invented in Saudi Arabia, actually. I don't know why I know that, but I'm like almost certain that that's true. So, fun fact. Let's touch on basic geometry here, and then let's just do one iceberg and then the other iceberg. That makes sense, right, Adam? Yeah. Okay, let's just knock everything out here. So basic geometry. What is basic geometry? let's keep that explanation. I'm going to keep this explanation really simple. There are circles, squares, triangles. There are shapes, okay? And then with these, because I want to keep this like as simple as I can right now. And there is a lot that could be said about geometry. And so this is saying basic geometry. I guess we could talk about the Platonic solids. I could touch on those real quick. So these are the Platonic solids. They come from ancient Greece, and basically they're special because this has 3 sides, this has 4 sides, this has 5 sides. You know, what you can do is have all sides be identical and still have these nice shapes. And all angles are the same, all edges are the same. All of these are regular polygons. So, a polygon is just a shape with has edges and sides, right? Or edges and sides are the same thing, sorry. Points and edges, right? I think that's all I want to say about basic geometry right now. Let's see. Let's do order of operations. So we know about addition and multiplication. Now let's say we want to do something like 2, 3 plus 1 plus 3 times 2 plus 1. Okay, so what order of operations is PEMDAS. Oh, let's square that. That's really annoying, but whatever. Actually, it's not algebraic, so it's fine. Multiply, divide, P parentheses, E exponents, M multiply, D divide, A add, S subtract. So what does that mean? The order of operations says to do everything in the parentheses first. So what would that look like? Well, now what does that look like? I feel like I keep saying, what does that look like? And so let's spell that out. Perseverance. What's that stand for? P. Perseverance. Now, I know what you're saying. Adam, you can't start an acronym with the same word, but to that I would say you need perseverance. So that's a 4, right? And then that's a 3. And so that's our parentheses step. Now, what's next? Exponents. We didn't talk about this. Well, we talked about this with the 3 times 3 thing, right? Where it becomes the square 9, right? So this is the exponentiation. We're squaring it again. So what's 4 squared? If you did the square and it was 4 by 4, right, you'd get 16. So this becomes 16. Next is multiplication. So you multiply these within the parentheses, you multiply these things. So this is 3 times 3, which we know is 9. And then 2 times 16 is 32. So we get 32 plus 9. PEMDAS, so that's multiply or divide. We didn't have to do any division, so we don't have to worry about that. And now we're doing our adding and subtracting. Now we add 32 plus 9. I think that's maybe 41. I'm not going to check my work, but I think that's 41. So that concludes our lesson on order of operations. Next, decimals. So, okay, we'll talk about division for this. What is 7 divided by 2? That is 3.5, right? So you can't represent something as a whole number, and so you have to represent it as a decimal. You know what I mean? Or like things with money, you know? Everything has dollars and cents. Cents is just what's in the decimal place. And yeah, that's decimals. Factors. And 10 out of 10 confidence on everything I just said, by the way. Except for my addition, but I'm pretty sure that's also correct. Okay, factors. Let's take a look at this 2 times 16 again. 32 is 2 times 16, but it's also 2 times 2 times 8, which is also 2 times 2 times 2 times 4. So you can keep factoring out these 2's. The fact that you can break this up, this 32, up into multiple things, called factoring. It's kind of an extension of division if you think about it. And yeah, that's that. Powers, we talked about powers with the 4 squared situation equals 16. So if we wanted to do, say, 3 cubed, that would be, what is 3 cubed? 27, and that's if you want to think about the 3 by 3 thing, right? What if you take that in another third dimension? Imagine that's like a 3-dimensional cube, right? And now you're counting the volume of the cube. It should be 3 cubed. So you're counting the volume of the cube now. And so the fourth power is just doing this in a higher, like in the fourth dimension, if you want to think about it that way. So exponentiation, don't think about dimensions too much, but that's where it comes from. It's really just the concept of being able to make numbers. I would say it's the simplest way to make a number bigger. That's what you need to know about exponentiation at this level. Or powers, exponentiation, same thing. Cartesian coordinates, that's graphing coordinates. So we have like how you have a graph like this, and it has, that's 0, 0, even though those don't look like zeros, but it's 0, 0. And then like this is like, so this is the x-axis, this is the y-axis. Things are written in x comma y coordinates. So if in this case where it's up here and like, but straight up, that's 0 on the x and 10 on the y. And likewise, or not likewise, but inversely, this is 10 on the x and 0 on the y. And then you can have a point in the middle here that's 5 on the x and 5 on the y. And that's how you get graphs. And then you can, you can make lines on these, and then you get functions, which we're going to talk about next. So let's just talk about this now, where you get something like this, at y equals x. It's this line where if whatever you plug in for x here, say 5, spits out a y of 5, or 1 goes to 1, or -1 goes to -1, and you get this line here of y equals x. Let's see how much of the iceberg that helped cover. Oh, perfect, because that's equations. Nice, equations. And then also 10 out of 10 confidence on that. Cartesian coordinates, by the way. So this is interesting, actually, because Cartesian coordinates weren't discovered until like Descartes was like the 1600s, I want to say, was when, Cartesian, like just coordinate systems were like normalized, right? And what's interesting about that is that like, so take this for example. Well, actually, I don't want to get ahead of myself, but we'll talk about it later. But the things like, people could prove things like, the area of a triangle and stuff like that way before that they could like put it on a graph and like show it like that. You know what I mean? Like before, like, I don't know. I just feel like it's way less obvious to evaluate things without coordinates because like you have measurements, but then, that's all you can just compare measurements, and like you need a 3-dimensional space to do it. Whereas Cartesian coordinates can go into an n-dimensional space and, they open up a lot of, what were previously limits. So, and that didn't happen until like, it's like between the 14th and the 16th century, somewhere in there, like I want to say. But maybe I'm not confident on that. I give myself a 5 out of 10 on confidence for that. Seriously though, it was a big, like, and he's a philosopher. He wasn't even a full-time mathematician. So yeah, big dub from Descartes, shout out. And yeah, let's move on to radicals. I think a radical is just like, I know what a radical is. I don't know what they, like, I think what they're referring to is like the fact that like, okay, well, we'll talk about this too. So like the square root of 2 is like, so the square root of 9 is 3 because 3 squared equals 9, right? We talked about squares, right? And then you could take the cube root of 27 and you would get 3 because 3 cubed is 27, right? So if you want to think like it kind of rearranges these things. It puts this over here and then gets this alone, if that makes sense. It's a way to rearrange things. And then they also, I think the next thing here is irrational numbers. Perfect. Irrational number. I don't know what pre-algebra is, by the way. Let me Google what pre-algebra is because, okay, so basically pre-algebra is everything that I've taught you so far, honestly. The only things that were maybe left out were the Pythagorean theorem, which is a squared plus b squared equals c squared. And that's for the sides of a triangle. This is a... Wait, is that right? I had to double check myself for a second. No, that's right. So this is c, this is a, this is b. And a squared plus b squared equals c squared is the way to find the length of each side of the triangle. This is a 90-degree angle, which just means it's yeah, you guys get it. It's square, right? So, and then the other thing that pre-algebra says is that like the area of this shade, like the area of this shaded region equals 1/2 base times height, where this is base and that's height, but this is just the height of the triangle and this is the width of the base of the triangle, and that gives you the area. And then think about it like this: if it was a rectangle like that, it wouldn't be 1/2, it would be the whole thing, because it'd be h times b, but instead it's only half, so it's 1/2 base times height. That's the area of a triangle. That's pre-algebra for you. So sorry, we got off track. What's the next thing? Oh yeah, irrational numbers. So say you want to do this square root thing, right, where the square root of 9 equals 3, but you want to do that with a number that doesn't work like this. So you want to take the square root of 2. And now the square root of 2 is like 1.447, maybe, something like that. Somewhat confident on, I'm 10 out of 10 confident on the 1.4 of this. Okay. Maybe even the 0.44, but yeah. So that's the concept of an irrational number. They cannot be, an irrational number cannot be expressed as, because a rational number like 3.5 can be expressed as a fraction, like 7/2. But an irrational number like this there's no a over b that will ever equal square root of 2. So it's called an irrational number when that happens. And you know, there are more irrational numbers than rational numbers, so it's real fun. Variables, equations, and functions are the last 3 pieces on this iceberg, right? So variables are something like x is a variable, and it just means it stands for something. So like x is apples. That's a variable, right? And then what were the other 2? Equations and functions. So an equation would be, so say an apple is $3. And then say we have 5 apples, how many dollars is that? So, and then the equation for that is 5 apples times $3 per apple is $15. And that's an equation. And then the function would be to say it's $3 per apple and we have X number of apples, and that equals Y dollars, right? And it's really hard to write, but yeah. So then the equation y equals 3x, and we talked about equations earlier with when we graphed, right? So now y equals 3x. On the graph, that's more of a slanted upward like that, whereas opposed to y equals x was like that, you know? So that covers functions, equations, and variables, and brings us to the end of that iceberg. Now let's see what we missed on this iceberg, because this one is a little more detailed, but this iceberg has more general knowledge, has better detail for general knowledge, right? Whereas this iceberg really, like, it runs a lot deeper. So that's why we're doing both. And so with that, we will start covering iceberg number 2. So numbers, addition, zero, subtraction, we've all covered. Rounding is simply the concept of like you have a fraction that can't be expressed as a whole number, but you want a whole number, so you round up or down. So it's a way of getting from a decimal like 3.7 or 3.3 to a whole number. So 3.7 is closer to 4 than it is to 3. So you round up, and that's 4. 3.3 is closer to 3 than it is to 4, so you round down, and that's 3. That's all rounding. That's why it's so high up on this iceberg. So rounding, multiplication, fractions we've talked about, division we've talked about, lines we've talked about, y equals x, that's just a line. Lines go on forever. That's a fun fact about lines. Give myself a 10 out of 10 confidence on that. Okay, so we talked about fractions, like 3/5. No, 3/5 isn't a fraction that we talked about, but think about 3/5 as a fraction. Where was I going with that? I got distracted. I was like, I was trying to, whatever. I was trying to not make a joke, and then I got lost track, So, fraction 7/2, right? This is the top number is I'm just going to go it's the numerator and the denominator. I can't write much better than that. But the numerator is simply the top of the fraction. The denominator is the bottom of the fraction. It's just a simple division situation, and yeah. That's the numerator and the denominator. Percentage. So a percentage is just a way of writing a decimal. Think about this. If you have, let's go back to 3/5. If you have 3/5, that's 0.6. And then now if you multiply this by 100, it'd be 60%. And what that's basically saying is like 3/5 is 60% of 5, right? Which is true, right? And that's what a percentage is. So we did remainder. Okay, this is a and then okay, it says term, just TERM. That's literally just anything. You can refer to basically anything as actually the confidence on this isn't that high, but to me, as somebody who studied math, basically anything is a term. Any variable, a variable is basically, it's the same thing as a variable, a term. It's just something that you are referencing or using to represent something, or literally just anything. I don't even, fun fact about that is I don't know why it's on the iceberg other than to throw me off and make me look like a dumbass while I'm trying to look cool in front of my friends. But all right. Anyway, moving on. Remainder. So let's go back to the 7/2. Now we get 3.5. So what this is, if we have 7, we have 3 groups of 2. So we have 2, 2, 2, right? And then we have one more left because we've been dividing by 2. Okay? So now, but we have this 1 all by itself. So this is, you could say 7/2 is 3 remainder, and that just means that the decimal attached to that is 1/2. Or if it was 7/3, it would be, I don't know what 7/3 is actually. It's like 2 1/3, right? So that's 2 remainder 1, and that's 2 1/3 is what that is. Or I think that's 7. Yeah, that's 7/3. Okay, so that's what remainders is, and remainders are actually very important. Way later. Next month from now, we'll be talking about what remainders really are, but you don't have to worry about it until then. I do. So, yeah. Everybody, yeah, get excited for me. Denominator, percentage, line, we've covered. Square, we've covered. 3 times 3, that's squaring. Volume, that's cubing, right? Like we talked about, the cube. And then counting the squares in the cube, that's the volume. Mean is the average. So, see, why is this? It's weird that it's kind of weird that this is up here, I'm not going to lie. So, mean is the average. I guess we'll just, like, you've heard of the average before. I guess we'll do an example. So let's say we have 1 plus 2. We have this set 1, 2, and 3. And then we want to know what the mean is. We add 1 plus 2 plus 3. And then we divide by the number of numbers that we just added. So we have 1 plus 2 plus 3, that's 3 numbers. So you divide by 3. And then this becomes 6 over 3, which is 2, which is this kind of middle value here. It's the sum of the numbers divided by the number of numbers, which tells you the average size of the numbers, right? Does that make sense? On average, this is, because if you take 1 plus 3 over 2, you're only adding 2 numbers here, and that's 4 over 2. So the average is still 2, because it's the middle number, right? It's the mean. It's in this case, it's the halfway point between the 2 numbers, right? Okay, so it looks like the only things left at the elementary level are degree and ball. This one was clearly not written by wait a minute. This is interesting because a ball is here and a sphere is here. But based on what I know about math, a ball can be in any number of dimensions. It can be like, so confidence, 10 out of 10. Fun fact, a ball can be in any dimensions. So you can have a 10-dimensional ball, whereas a sphere is only in 3 dimensions and is always in 3 dimensions. So I don't know what they mean exactly by ball here, because balls are actually like kind of advanced mathematical objects and spheres are not. So like maybe we might talk about balls when we get down here to like topology, but that's it. That seems out of place to me right now. So I don't know why. Because I figured it was because sphere wasn't on here, but then sphere is right here. So I guess the last thing we'll talk about is a degree. And then I guess we didn't talk about circles. So we'll talk about circles and degrees here. So take a circle, and there's a lot to be said about circles. You could have complex circles, which we'll get to. So take a circle, and then this is like the x, and this is y. Or don't even think about it this way. But so this is a 90-degree angle. You start in the middle, and then you take a walk out, and then swing. You swing around, and then this angle here can be in either degrees or radians. There's no unit for radians. So this is basically just the angle of this difference can be because the whole distance around the circle one time is 360 degrees. So 1 degree is just one, like, by definition, there's not a better definition than this in math because degrees aren't really that used compared to radians. So the definition of a degree is 1/360th of the way around a circle. That's what a degree is. That's all it is. Maybe they're talking about temperature, in which case I'm not a meteorologist and somebody else can tell you what a degree is. It has to do with raising water Oh no, that's a calorie. It's like the can raise water 1 degree or whatever, like enough energy to raise water 1 degree. That's what a calorie is, right? Yeah, I don't know what a degree is. Sorry. Anyway, variable, we talked about that. It's just like x is the number of apples. We plug x into an equation. There you go. Sphere. We discussed that a little bit, but it's a three-dimensional ball. It's got, it's just a 3D ball. That's a 3D. The area is like, or the volume is like maybe pi 4. I think I'm right about this. 4/3 pi r cubed. I'm such a, because I give myself a 10 out of 10 confidence on 4/3 pi r cubed, and I don't know why I know that. I just like, that's just something that but yeah, so that's a sphere. It's 3 dimensions. It's real fun. And then r is just the distance from the center of this sphere, okay, the inside, the innermost point to the surface. That's r. It's the radius, and that's that. Absolute value. Absolute value is a very simple concept. So it's just, everything is always positive, right? So we talked about negative numbers. They don't exist anymore. The absolute value of 3 is 3. And the absolute value of negative 3 is 3. The absolute value of negative 100 is 100. That's all it is. Nothing can be negative. It's always positive. It's like it doesn't really come up that much in sophisticated math because it's a little bit of a hand wavy thing where it's just like, oh, it was negative, now it's not. You know what I mean? But the real way to do that would be to take the square, or like to square the square root or something, whatever. But yeah, don't worry about that. So sine, oh geez. So sine and cosine. All right. Well, I guess let's go back to talking about the circle here. Everybody acts like that's a normal circle. Okay. So now say we have a line like this, and this is a triangle that we have. And then this is, this distance and this distance are the same. Okay. So this would be a 45-degree angle. So we have this triangle, right? I'm going to talk about sine, cosine, and tangent all at once here. We have SOHCAHTOA. Say we have this angle here. This is the angle x. So sine of x gives us the ratio of opposite, call it A, call it C, call this B, is the ratio of A to C based on that angle x. It's funny because as I was spelling out SOHCAHTOA, I was like, do I remember this? But I do. I give myself a 10 out of 10 confidence for the sine function. Now the cosine function is, they're like cousins, they're like twins. They're like opposites, but they're the same, but they're a little bit different. And that is adjacent, which is this b. It's this. Think about x. The hypotenuse is always the longest side, right? So that's c. You can see that it's c, because this. So b is the adjacent. It's the one touching x. So this is b over c, and that's cosine. So it's this relationship between the angle here and the distance of the ratio of the distance between these sides. That relationship is sine and cosine, and those are going to come up a lot. Those are going to be, possibly kind of heavily used down the line for other things. So they're a little bit important to know, but they are just these. And then think about it like this too. So take this triangle, for instance, on this graph. Sine is always opposite over hypotenuse, right? So it's always this side over this side. A triangle can be like straight up like this, you know what I mean? And then, so sine can only go that high, right? Or it can only go this low, right? And same thing with cosine. It can only go out that far or that far. It's bound by the circle, though. So it will always, like in real life, sine and cosine functions will always spit out a number between negative 2 pi and positive 2 pi. Because that's all that the ratios can be. So, yeah, there you go. Or wait, is it just one? Sorry, they'll only spit out a number between 0 and 1. They cycle every 2 pi. So like x. This is what I'm trying to say. This is what I'm getting at. Cosine of these are cyclical functions. So cosine of x plus 2 pi is equal to cosine of x. They're the same. A sine function and a cosine function both look the same on a graph, and they look something like this. But this is like they're the same height every time, and this distance is constant. Same distance every time. So that like these are very well behaved functions, and yeah. Oh, it didn't even say cosine. It said cone. Oh no. Well, you got a that's my fun fact, is what a cosine is. Sorry about that, folks. Jeez. A cone. What do you want me to say about a cone? It's like that, and then it's like that. It's like a birthday party hat. That's a cone, I guess. And then like this has a height, and this has a radius, and then this has a kind of slope from the center point, this radius here, to the outside point. A slope that's based on what the radius height ratio is. Okay, and then let me look up the volume of real intuitive. Pi r squared h. That's h over 3 is the volume. So I don't know, like, it's there. We're knocking the iceberg out. That's a cone. They don't come up much in math. They're just kind of things that, they just exist. So I'm glad we got that taken care of. I'm trying to think of a good way to knock these things out efficiently. I guess we're just going to keep going like across, down and across. Okay, so a polynomial. God, see, that's so much more advanced, though, than like... Okay, whatever. We'll just do it. Because we've already talked about things from the first iceberg, so we're equipped with the tools to handle this, folks. Okay, so remember the apples equation, where we said that that's a function, right? So there's no good example. Like I guess because I have an economics degree too, but I guess I'll give an economics example where you are much more okay with working an 8-hour day than a 16-hour day. So the cost of you working a 16-hour day is more than just double the cost of you working 2 8-hour days, right? Because it becomes, the longer you're there, the more grueling it is, and the more you don't want to work, and the less you're, so you're less productive, so it's costing more, and there are diminishing returns on that, right? You could say the cost is getting exponentially higher, right? So a polynomial would represent something like that, where like x is the number of something produced. Okay, it can still be apples, actually. It's the number of apples picked. Say that there are more apples to be picked than there are apple pickers, and so the apple pickers are working overtime, and they have to get paid for. You have to get paid for overtime. Period. That's what's going on. So the cost per apple is going to get exponentially high. It's going to grow with the number of apples you need. The more apples you need, the more expensive each apple is going to get. So let's say the total cost of apples it's still this $3 per apple. That's what it costs, but it's also x squared plus 3x equals y, and that's the new cost of an apple. So the more apples you buy, the more expensive it's going to be per apple, right? And it doesn't like, and it's actually a terrible example because if you buy in bulk, then it's cheaper. So I ignore everything I'm saying. But the function, the equation is the important part. A polynomial is an equation that has an x term and an x squared term, or an x cubed term and an x term. It's any of these, and then you can also write y as f of x, just meaning it's a function of x, right? And so that's what a polynomial is. And then what you would do to solve something like this, typically when it comes to polynomials, what you do is you solve for 0. So we have x squared plus 3x. And then you typically solve these for 0, so 0. Now what you can do is, remember we talked about factoring. So factor out an x, you have x plus 3 times x, right? So, because you can redistribute this x out to both things, and you get this original equation back. So that being said, this means that x equals 0 and x plus 3 equals 0, which means that x equals negative 3. So this function, x cubed plus 3x, equals 0 at x equals 0, negative 3. Those are and because this is a x squared problem, that means they're like a polynomial of degree n has n solutions. So, we are not going to solve this equation, by the way, because I just realized what that's going to look like, and it's way too difficult to describe right now. But x cubed plus x is still a polynomial. But yeah, that's... Hello?
Hey.
Hey, I'm recording my video.
Oh, my B.
Yeah, you're on speaker, but you're getting cut because it's getting really long.
Jeez. Alright, good luck.
I'll text you, miss.
Alright, I love you. Bye.
Love you, bye. Confidence on this, by the way, 10 out of 10. Inverses. Okay. Let's go back to 7 halves. The inverse of 7 halves is 2 sevenths. And like you could write an inverse like this, like 3 to the negative 1 power. Because we did like to the second power, to the third power. Okay, let's go. If you go, well, let's just establish. If you go to the first power, that's just the number. And then any number to the 0th power is always 1. It just is. It's just a fact of math. Okay. So that's 0, but we can go negative numbers too. So we can go 3 to the negative 1. And 3 to the negative 1 is just 1/3. Bring the number down to the... Remember we were talking about numerators and denominators, folks? We bring it down to the denominator. The numerators and denominators flip. Because if you think about what is 3? 3 is just 3 over 1. So now it goes to 1 over 3. And that's an inverse. A prime number. Here we go. Okay, so a prime, the first few prime numbers, 2, 3, 5, 7, 11, I want to say. Okay. What do these numbers have in common? There is no number other than 1 that you can divide these numbers by to make them any small. Like these numbers cannot be factored. They cannot be made any smaller whole numbers. 2 is the only even prime number because every other even number can always be divided by 2. So none of them can be prime. Something like 9 can be divided by 3, so it's not prime. 6, you can divide by 3 and it equals 2. You can divide it by 2 and it equals 3. 6 is not prime. It's, you know, whereas these other numbers are prime. And fun fact about confidence 10 out of 10, by the way, fun fact about primes is your credit card number is just two very large prime numbers multiplied together, because it's very hard to figure out what those numbers are if they're prime numbers, and there's only two prime numbers multiplied together, so you can't divide it by 2, right? So right, like, I don't know, maybe your credit card number ends in 2. I'd be kind of surprised, actually, but actually mine ends in 0. So, but it comes from this kind of thing. Like, this is how encryption works, but it comes from multiplying together large prime numbers and then, probably adjusting digitally to, like, make routing numbers work and stuff like that. But like most encryption comes from just like multiplication of prime numbers that are 25 digits long, because they're an infinite. It's like easily provable that there are an infinite number of prime numbers. So there will, like, there exist prime numbers that are hundreds of digits long, and like they find new largest prime numbers like all the time. So it's an ongoing field of math. It's a very complicated field of math, but it's like like prime number theorems, or not the prime number theorem, but there are a lot of theories about prime numbers that are very advanced. Okay, median, that's just the middle number. So remember, so if we have a list 1, 2, 3, 4, 5. The middle number is 3. It's the median. Confidence 10 out of 10. If you just had 1, 2, and 3, 2 would be the median. And you can find the median easily just by, like, if you have a list of numbers, cross out the outside ones first, then cross out inside one more, and keep crossing them out until you're left with the one in the middle, and there's your median. If there's an even number of numbers, then you have 2 medians, I believe. You just call them both the median. I don't think you find the number that's, like, I don't think you find the average of them and then call that the median. So I think there are just 2 medians if there's an even number of numbers. And that's what a median is. Comes up in statistics a lot. That's my fun fact. Sector? A sector. Okay, I think all that's referring to is when we were talking about the area of a triangle right here, 1/2 base times height. This, like, the sector is just like, okay, you have a square, you're going to take half of it and shade it in. That half is the half. It's a sector of the whole thing. I think that's all that they're talking about with that. Probability. That comes back to the percentages kind of too, where probability is like p of x. What can I write about probability? It's bounded by, it cannot be less than 0 or greater than 1. Okay, that's so it's going to be a percent, like it's like a percentage of something happening, like a percent chance of something happening. So probability of heads in a coin flip is 1/2 or 0.5 or 50%, right? That's probability. And probability theory can get a lot more complicated than that, but those are the basics of it, and I think that, like, that's all that we have to touch on at this point, because like the random matrices stuff is also probability theory, but that's not for another few weeks or so. So constant, that's just a number. That's just a number that doesn't change. A variable, right? Like the number, like 3x. X is the number of apples. X is a variable. That is not a constant because it changes with the number of apples. The constant is just a number. It doesn't change. It just is what it is. A function, we've talked about functions. The number of, like, y equals 3x, that's a function of, $3 per apple. There's the polynomial thing we also touched on with the zeros. That's a function. These are all just different forms of functions. Remember that I said this f of x, right? Anything f of x is a function. Or you can also have functions of x and y, and you can, but at this point we're just talking about functions of x. Coordinate systems, that's that Cartesian stuff we talked about. Square roots, that's that radical stuff we talked about. Pi, we will get there. So let's see, the Pythagorean theorem. I think we discussed. It's the C, A, and B. A squared plus B squared equals C squared, and that's so by knowing the length of two sides of the triangle, you can always find the third, because like C squared minus B squared equals A squared. So you can rearrange this, however which way you want, and it's one of the oldest theorems in the book. 10 out of 10 confidence on that, and by our old friend Pythagoras back in the day. So yeah, square root, coordinate system, we got all that. Okay, so we got negative number. We've a hexagon. I don't know what it wants me to, like, I don't know what there is to be said about a hexagon, to be honest with you. Like, I mean, like, yeah, it's a six-sided figure. Here, you can watch a little drawing of it there. But like, I'm lost on what needs to be said about this. There's, you can find the area, apparently, based on the, like, okay, whatever. Based on these different radiuses. So that's fun. That's a fun fact about hexagons, I suppose. And hopefully they're six-sided, you know how you can have a shape with any number of sides you want? A hexagon is what you get when you have six sides. That's all that is. Proportionality, that's a percentage. It's just a relationship between two things. Like, it's like each apple is $3. Proportional, like, the proportion of dollars to apples is 3. 3 for each one. The proportion of apples to dollars is like a third of an apple would be $1. Or like, what proportion of people drive cars? It's just what percentage of people have licenses and vehicles. Proportions. It's just a relation between two things of different, a way to compare two things of different measure. Okay, pyramid, again, much like hexagon. I don't know what they want me to say about pyramids, rather. Yeah, see, great. It's, okay, can we get a math pyramid in the geometric sense? All right. It's just, everybody knows what a pyramid is. Why? Like, I don't know why this is on here. I guess you could say that it has two n edges, n plus 1 faces, and n plus 1 vert. We could talk about that, but that's I don't know. We just don't need to right now. It's not that, they don't really come up ever, pyramids, here's a pyramid in n dimensions. That can be, that's fun. But everybody knows what a pyramid is. All right. And that brings us to our last entry on the introduction to the mathematical iceberg, which is pi. So pi is, here we go, last thing. 3.14 something. It goes on forever. It's like similar to the irrational numbers that can't be written as fractions. This also cannot be written as a fraction, but different from the square root of 2, which can't be written as a fraction. This can't be written as a representation. Like, pi itself can't be written as a number, like with a numerical representation. Because this at least has a 2 in it, right? It's just pi. It goes on forever. There's no numbers that can properly really describe it. So yeah, that's pi. And what is pi? Pi is the relationship between the radius and the circumference. So the distance around the circle, I'm drawing this horribly. My pen is breaking. So the circumference of a circle is 2 pi r. And this is how, if you know what the radius of a circle is, right? And you know what the circumference of a circle is, you find what pi is. Pi is discovered as the ratio of the circumference to the radius. Equals 2 pi, and 2 pi is also known as tau, but whatever. It's just like, 2 pi is known to be the radius, or the ratio between the circumference of the circle and the radius of the circle. And that is pi. My pen is breaking. I'm going to have to get a new one for part 2. But it's okay. It worked out. So yeah, that was a lot of information and a little bit of information all at once, I feel like. I don't know. I hope that everybody enjoyed that. I think that it's tough because I started with multiple sections, so the next parts should be shorter, but at the same time there's going to be more to explain, so it's tough to know. But I hope you guys enjoyed the video. I hope that was, entertaining and helpful in some way. Maybe you learned something, maybe you had a laugh along the way. I don't know. But yeah, if you enjoyed, leave a like, remember to comment and subscribe. And yeah, I will talk to you guys later. Love you, and I'll talk to you soon.